coming there. Okay, thank you everyone for joining the event today, and also thank you, Professor Metin, for accepting our invitation to be the guest speaker for today's talk. Thank you, Professor Halim, also to giving us the opportunity to have this event. So, for those of you who don't know me, I just wanted to also introduce myself that I'm the PhD candidate and also contract instructor at Carleton University. This event is co-organized by Carleton University Non-Terrestrial Networks Lab and also IEEE Women in Engineering Ottawa. And I'm the chair for IEEE Women in Engineering Ottawa and also the vice chair for IEEE Young Professionals Ottawa. These are the links to the to my LinkedIn and also IEEE Women in Engineering Ottawa. And we will post our future events also on LinkedIn. If you are interested, you can get connected. And also, I would like also to introduce Professor Metin, but I think it's better to pass to Professor Halim, and maybe Professor Halim can also introduce Professor Metin, and then we will start by Professor Metin. Thank you.
Thank you, Afsun, and hello, everyone. It is such a delight to have the opportunity to introduce Professor Metin Ozturk from Ankara Yıldırım Bayezid University. I actually am on the go at the moment at Toronto Airport, so I wanted very much to be present, at least in the beginning of this webinar. However, 5 minutes after it starts, I'll take off because I have a flight to catch. Metin, our acquaintance with Metin has a history from literature. Having said that, between, I'm now trying to remember the dates, from October 2023 to October 2024, for one full year, my lab had the pleasure to host Metin at Carleton University as a visiting professor, and this visit was funded by a competitive mobility grant awarded by the Scientific and Technological Research Council of Turkey, TÜBİTAK, equivalent of NSF in the US. We can just call it Turkish Science Foundation. That initiated a lot of collaboration in a variety of research streams, mainly in non-terrestrial networks. And one of the areas that Metin has great expertise is AI ML, the topic of today's presentation. So with Metin, we explored in what ways we can employ this new tool, at least that I have been trying to understand as a user in emerging networks of the future. Lots of good papers came out, and many others are brewing or under review. So keep an eye in the literature. Our co-authored papers, Metin also with me has been co-supervising a number of Carleton team members. I should also add that just to complete the story, two of Metin's students also visited Carleton University for durations of, I believe, 6 months. And many good works came out of those as well. So basically, maybe I should stop by saying that we have a legacy of hosting scholars around the world at all levels, from undergraduate to master's and PhD students, postdoctoral fellows, and visiting professors like Metin. If you are interested, let us talk about that to find an appropriate mobility fund. I also thank very much to Afsun. Afsun is the coordinator of the Non-Terrestrial Networks Lab at Carleton University. She has several hats, as she mentioned. She is the chair of Women in Engineering in Ottawa and an officer of several IEEE chapters in Ottawa and Canada. we are organizing this event jointly. I generally post webinars and seminars in the group in LinkedIn, my LinkedIn feed. You might keep an eye there for future events. The future events include a webinar next week, next Wednesday on 30th, a testbed demo for satellite mega constellations. The information is already in my LinkedIn. After that, we will have an IEEE distinguished lecture, which will be in person. And right after ICC on 3 days, actually, or 2.5 days, June 15, 16, 17, we will have a 3-day in-person workshop at Carleton University Non-Terrestrial Networks Lab uh, on future connectivity technologies. Once again, thank you, Metin. It's a pity that I won't be able to stay until the end, but certainly I will watch the webinar from YouTube. To you, Afsun.
Thank you very much, Professor Halim. So now I think Professor Metin, if you are ready to start. And also for the attendees, feel free to post your questions also in the chat box. And also at the end of the webinar, we will have a section for the question and answer.
Shall I start, Afsun?
Yeah, of course. Thank you.
Okay, thank you, Afsun, for organizing this. Actually, thanks to IEEE Women in Engineering Ottawa section and also Carleton University Non-Terrestrial Networks Lab, which is led by Professor Halim Yanakomeroğlu. I also specifically thanks to Afsun for the nice invitation. Actually, in the participants, I see many friends, colleagues, and students. So then it is very nice to be here today. So before we start, I just want to start with a question as a refreshment. So then what is AI? The question is this, so which is very relevant to today's topic. So in your perception, is AI this, something that can take your job from you? Or AI is something like this, which is not capable of doing very sophisticated task, which is very in the first stages of its development. Or AI is this something to sell the products to other people, like we have seen in the literature as well. So then we have AI empowered, so on and so forth, algorithm to solve these and such problems in wireless communication. Which one is AI actually? This is the main question. So my name is Metin Ozturk. I am from Ankara Yıldırım Beyazıt University. I work as an assistant professor of telecommunication there. So as Professor Halim nicely mentioned, I had the pleasure to be with the Carleton University NTN lab last year for a full year. So actually, today's content will be something like this. So then I will start with recap on like some backgrounds on AI and ML, different AI and ML methodologies. So then what is 6G? What are the visions and standardizations? So then what AI can bring in the table related to 6G. And also I will talk about some use cases, our works, and some other interesting topics that can like where AI is implemented in orchestrating wireless networking. So then I will also talk about the role of generative AI, which is very hot topic these days, how generative AI can improve the performance of wireless networks, specifically 6G networks. I will also mention challenges and future directions. So let's start with the recap on AI or ML. So before we start, so there is a confusion even in my previous slide. You said you have seen that it is AI slash ML. So then are they the same thing? Actually, I have seen that there is a huge confusion between in the literature, in the media, everywhere there's a huge confusion. What is AI? What is ML? So then they are mostly used interchangeably, but let's see if they are the same thing. So basically, they are not the same thing, but they are very close to each other. So yes, you might have seen in the literature, in the media, that AI and ML, they are used interchangeably, but actually they are not. So what are the differences? So actually, AI, so ML is the subset of AI, I would say. So then AI is a broader concept. It is a concept that we want to simulate the human intelligence. So this is the definition of AI. So this is the concept we want to simulate the human intelligence. So on the contrary, machine learning is one way of doing this. So it is not how we can mimic or how we can simulate the human intelligence. It is a way towards achieving the artificial intelligence. So then in AI, we can develop some smart systems that can perform some specific tasks. But in ML, machine learning, we learn from data. We learn the patterns of the data. So in AI, as I said, AI can include ML, NLP, natural language processing, robotics, expert systems, computer vision, etc. So the thing is that when it comes to AI, it doesn't have to be data driven. There, it doesn't have to be learning. So there shouldn't be learning. So learning is a must for machine learning. It is always data driven. So then there is a learning, there is an experience building in machine learning. But when it comes to AI, so it is not a must. So as we see on the slide, there are some expert systems, for example. They are not basically machine learning algorithms. They are not building experience, but they are also they are still mentioned within the category of AI. So the thing is that AI is the umbrella term, but the ML is the practical component, practical tool for us to achieve what AI is promising. So what could be different categories of machine learning? So then the first one is the supervised learning. So then I will explain them in detail shortly. So then unsupervised learning, reinforcement learning, deep reinforcement learning, federated learning, generative AI, agentic AI. So then there are lots of names. So then therefore there are different categories. There are even more than this, but these are just the very common ones in the literature. So let's start with the supervised learning. So supervised learning is the machine learning algorithms, set of machine learning algorithms. So the main idea is we have input data, but the input data is labeled. It means that each input data is associated with an output data. It is labeled. So just like teaching a child, for example, this is apple, this is pear, this is orange. So then when you show them an orange, so then you say that this is an orange. So when you show them the orange, so this is the input vision for them, and also for computer as well. So then at the end, you are saying, okay, this is the orange. So then this is the supervision part. So then you are supervising the kind of system. This system could be a computer. This system can be a human being as well. So inputs are the main components. Like as I said, it could be a picture of anything. It could be, as I said, it could be a picture of orange. It could be a picture of apple, trees, whatever it is. So then we are labeling them outputs. So then this is apple, this is tree, this is pears, etc., etc. So then there is a model. Model is the mapping between these inputs and outputs. So on the left-hand side of the system, which is the input part, there are features like the images in our example. So then at the output, there are the labels like oranges, apples in our example again. So the model is something that is mapping the inputs to the outputs, how inputs and outputs are correlated. This is the main task that we try to do in the model part. So then we are trying to modeling, we are trying to map the inputs to the outputs. So then loss function is a kind of measure that we use to identify the difference of what we estimated and what is the reality. So it is our basically performance. It is the performance of the model. So based on this performance, so the model keeps update itself. So like until it converges or loss function comes to an acceptable level, for example. So then there are some common algorithms. I won't go in detail about them. But there are linear regression. So there are logistic regression, decision trees, support vector machines, k-nearest neighbors, and artificial neural networks. Actually, among these, artificial neural networks has a special place because they are kind of founding algorithms for many sophisticated and strong, powerful recent algorithms like deep learning, even generative AI algorithms, etc. So then there are different applications of supervised learning. Spam email detection, for example, is a very classical example. Fraud detection, medical diagnosis, image classification. So what we try to do, the goal is we try to learn a function. Function is the model here. So uh, that can model, that can map the inputs to the outputs. So then there are two classes of supervised learning. One of them is classification and the other one is regression. The main difference is in the classification part, we predict the categorical labels, which are discrete values. But on the contrary, in the regression, we predict continuous numerical values. Uh, so as you see on the left-hand side figure, like there is an orange and apple. So then when you show the algorithm the image of orange, for example, so then you give the image as an input, then you say that this is an orange. So because the number of fruits that we have are finite, so then this is kind of categorical output. But the important catch here is that the inputs don't have to be categorical, they can be continuous, but the output is categorical here. On the contrary, for the regression, inputs have to be continuous and output also continuous as well. If the inputs are not continuous, so we need to map them to a continuous value. There are some methodologies for that to map the categorical values into continuous value. So then what are changes? The evaluations are changing here. So between classification and regression. For classification, we use accuracy, precision, recall, or sensitivity, F1 score. But when it comes to regression, we use root mean square error, R squared score, etc., etc. Different evaluation techniques are there for two different classes of supervised learning. So unsupervised learning, this time we don't have the supervision. It means that we just have the inputs. We don't have the outputs. So we just have the input data which are not labeled. So like this could be the positions of people, for example. Based on this, we are feeding our algorithm with these input data, which don't have labels, which don't have outputs. So then we expect it to find the hidden patterns inside this input data. So what can be done? Like clustering can be done with this. So then we can cluster the input points, input data by using unsupervised learning algorithms. Like there is a very common algorithm for this, which is k-means algorithm, for example. Imagine you are like the users in the wireless communication field terminology. There are some users distributed around the specific location. So then we want to cluster them. So then based on this cluster, we would do some further processing. Based on that, for example, we would do some base station orchestration management, mobility management, radio resource management, whatever it is. So then we want to cluster them. So then we just give the locations of users to the algorithm. Then it can iteratively cluster them by using k-means algorithm or others that you see on the screen. So then there is a dimensionality reduction as well. So dimensionality reduction means that so sometimes prior to these supervised learning algorithms, so then maybe I should say this here. So then these algorithms don't have to be individual. So then we can use unsupervised learning algorithms, but prior to that, we can put the data to unsupervised learning algorithm to do some initial processing. So like, for example, for this, so we are going to employ supervised learning algorithm classification, whatever it is. So then, but data has a lot of dimensionality, so it causes some complexity problems for us. So in such a case, we would like to reduce the dimensionality of the data, but without losing critical information. This is the main goal. So then there are some off-the-shelf algorithms for this, for example, principal component analysis, PCA. So these kind of algorithms can, with just given input data, they can reduce the dimensionality of the data. There are some association rules also as well, so I don't want to go in detail too much. I don't want to spend too much time on this. So that's why these are some main idea behind these unsupervised learning algorithms. What we can do customer segmentation for this, image compression and anomaly detection. So for example, when it comes to take the example of anomaly detection, so we cluster the data, for example, by using k-means algorithm. So when we give a new data to it, if it doesn't fit to the cluster that we have built with the data, historic data that we have, so then we can start questioning what is happening. So then is this data an outlier, or there is a problem with that? Or it could not fit into any cluster, or it could be very far away from the clusters, like even the closest one. It is very far away from the closest one, for example. Then we can start questioning what is happening, what are the problems. So then we can detect the anomaly. So there should be something malfunctioning in the systems that we have, for example. So that's why they are pretty important for wireless communication as well. So next class, next category is the reinforcement learning algorithms. So they are very special types. So unlike supervised and unsupervised learning algorithms, which are dealing with data, like historic data, I would say, in reinforcement learning algorithms, we don't have to do that. We don't need historic data to operate these algorithms, reinforcement learning algorithms, because mainly we use reinforcement learning for optimization purposes. So we want to optimize something in the network, for example, wireless network, like for example, antenna, tilt, for example, handover, mobility, radio resource management. We want to optimize something, then our option becomes reinforcement learning in this case. So then, because we want to use this agent-based or reward-based systems, what it does, so then we have an agent in reinforcement learning algorithms. It takes actions, it interacts with the environment that it is in. So then the objective is to maximize the cumulative reward. So then these are something that we design. Reward is something that we design. Reward is something that we want to maximize, for example. If it could be a penalty as well, it could be something that we want to minimize in the network. Like for example, handover frequency. We would like to minimize that, so then we would use penalty-based system. But throughput or sum rate, we would like to maximize it. So then in this case, reward-based reinforcement learning algorithm could be the option. So what are the key components? We have agent. Agent is the learner or decision maker in our system. It is the main guy. It is the entity that does all these things. So environment, so in our case, for example, it is the wireless communication environment. So a couple of base stations, hundreds of users, for example, in some certain, like for example, in Ottawa, we can say Ottawa can be our environment for this, or some small portion of Ottawa could be our environment as well. It is also dependent on what we are trying to do. So environment is where the agent actually operates. So states current situation of the agent. So then these are some hyperparameters, or these are the design components for us actually. So we want to design these things. What should be the state? What could be the situations? What could be the states of the agents? When it takes the action, it should change the state, but what should be this state? So then this state could be location of an individual user, for example. State could be the transmit power of one base station. State could be anything based on our needs, our problem at hand. So as action, as I said, it is something that agent does to optimize the network in specified field. Reward, as I said, it is like, for example, if you want to maximize the throughput sum rate, it could be the reward. If you want to minimize the energy consumption of the network, it could be the reward. Again, it depends on what we are trying to solve. Policy is the actual strategy that agent follows, how actions are taken, the how the experience is updated, I would say, how these things will happen, like how the agent will take the action, how it is gonna update the experience it has already built. So then these are the strategies, predefined strategies for these algorithms, and value functions. So then the future rewards for the agent. So then there are some common algorithms. They can be categorized as well. Value-based, like Q-learning, deep Q-learning, SARSA could be some of the examples for this. Policy-based, value-based, it means that it is based on the value. So then we calculate the value function as written on the left-hand side. We are pretty much interested in the value of the taken action. But for the policy based, we are trying to optimize the policy. We are trying to update the policy, optimize the policy. What could be the best policy for this agent to maximize the cumulative reward? So then these are the policy based approaches. So then there are actor critics and model based methods as well. So then DynaQ, for example, which is very pretty much powerful algorithm. So what can be said here? So then these could be on policy, off policy. So on policy means that it is following the same policy for updating the table it builds, for example, when it comes to Q-learning, and also taking the action, following the same policy. But off policy, they are not following the same policy. So Q-learning is an off policy method, for example, in this way. So actor critic, and there is also value function approximation, VFA. So there are some limitations of like value based or Q-learning, vanilla Q-learning algorithms. So because they store Q metrics, action state metrics, for all the states, for all the actions. So if the size of the problem is relatively small, so this is not a problem. So then you can store these metrics, right? But when states or actions are increasing, significantly, then you won't be able to perform the tasks because you would be out of the memory in your computer that you are doing this, in the machine that you are running these things, or it could take a lot of time to converge to something that is meaningful because of the computational complexity associated to these. So then for these kind of things, we have value function approximation. Instead of storing these tables, we are just estimating them by using some linear methods, by using some deep learning, for example, as in the case of DQN, or actor critic methodologies could be other options. So yeah, the learning group is this. We have agent taking actions goes to environment, and from environment reward and next state is calculated. Based on that, policy is updated. Then it comes to agent again. Agent takes another action. All this follows the same cycle until it converges. Deep learning is a subset of machine learning, or subset of artificial neural networks, I would say, or uses artificial neural networks. But what we say is that it has multiple layers. It doesn't mean that classical artificial neural networks have multiple layers. They can have multiple layers as well. But when we say deep learning, deep comes from there. So then there will be many hidden layers involved in the architecture of the artificial neural network. So this is one of the ways that we define deep learning in the literature. Other than that, so as I said, it is multi-layered architecture. Good thing is that it automatically extracts features from raw data. So normally we have manual operations. So to select the feature selection, there are some feature selection algorithms, for example, like PCA in unsupervised learning algorithm was one of the feature selection algorithms. But these algorithms do this automatically. I have struck out the first one. It says because inspired by the structure of the human brain. It is a very common things in the that you would see in textbooks, literature, everywhere. But personally, I don't believe that. So then, so we are creating some algorithm. Then we are trying to resemble it to some biological things. That's why we have these kind of things, because we can set it better in such a way. So image speak recognition would be one of the applications, natural language processing, self-driving, generative AI, which we will come shortly. Generative AI is based on these deep learning algorithms. What are the common architectures or common algorithms? Fully connected neural networks. So then these are the basic prediction tasks. So then these are very fundamental architectures. Everything is connected, all the layers with all the units, they are connected to each other. Then we have CNN, convolutional neural networks. Then we have recurrent neural networks for times. Yeah, for CNN we use it for image recognition or classification. For RNN, recurrent neural network, we use it for time series analysis. Then we have achieved to this LSTM, long short-term memory, because like it is also RNN basically, but because of some limitations of RNN, for example, vanishing gradient limitation. So then LSTM was built. So then it can make more accurate predictions in certain conditions. So last one, not last one, sorry. So deep reinforcement learning, again, as I said, when the network sizes are the dimension of the input is increasing. So like number of states, number of actions are increasing. So then the classical reinforcement learning algorithms like Q-learning and SARSA would not be possible, would not be feasible anymore. Then in those kind of cases, we would need deep reinforcement learning, where we would need to estimate the value instead of storing a matrix, action value matrix, for example. Then federated learning is a hot topic. Actually, it is not an algorithm. Federated learning is not like, for example, when we talk about supervised learning, we say there's ANN, there are different like support vector machines, so on and so forth. There are different algorithms. Like supervised learning is basically a set of different algorithms. Unsupervised learning, likewise unsupervised learning. So then k-means, SOM, for example, there are different algorithms. So then when they come together, we call them as unsupervised learning. Similarly in reinforcement learning. But federated learning is more like methodology, how we learn the things, how we update our model, how we exchange the data. It is not specifically an algorithm it is not a specific machine learning algorithm. It is more like an architecture. It is more like a procedure that we follow. So it is a decentralized machine learning approach. In this case, multiple devices or clients, they share a model. There is a global model, they share this model. The catch here is that they don't share the raw data. So that's why, so they just share the processed data or model parameters. That's why it is usually regarded as a secure network, secure way of performing machine learning algorithms. So when you have multiple agents, so if you have one agent in your system, you wouldn't need federated learning. But when you have multiple agents, so then they can run their algorithms in a distributed manner, like independent from each other. So that each can build its own model and make the predictions, optimization, etc., etc. But sometimes, and also most of the time, this is not an efficient way, because the amount of data that one agent can acquire is limited. And also it is not diverse. This is the problem. So then it has the generalization problem. The data that only a single node can acquire is usually not diverse and limited in terms of the amount. So in such cases, we can have multiple agents. So then each, for example, these agents, for example, take these agents as base stations in your network. Each base station can be one client, one device in your case in federated learning. So then they are building their own local algorithm, own local models. But at the same time, they are sharing this information, model parameters with each other so that they can acquire the data from other base stations. So, for example, one base station located in the city center can get an update from a base station which is located in a rural area. So then diversity increases significantly in this case. So then, and also the amount of data. So imagine the amount of data that a single base station can acquire, and compare with the networks like hundreds of base station combined. When hundreds of base stations combined, the amount of data would be much more than the single one. So then the amount of data is also increased. So then these are the things that can be used to increase the accuracy of the machine learning algorithms or models that we are building. At the same time, diversity can provide, again, accuracy, provide a performance boost in our case. So then, as I said, these are mostly regarded as privacy preserving algorithms because we are not sharing the raw data. For example, there could be some sensitive data that shouldn't be shared, like user data for my data, for example, my profile, location, credit cards, etc., etc. Those could be shared, but when it comes to federated learning, they are not shared. Instead, the model parameters, which don't have any meaning by themselves, they are shared. So then it is more secure. So then these things are aggregated at the central point. So then there's an aggregation, different aggregation algorithms, averaging, or some adding some regularization, etc., etc. So then comes to generative AI, which is very popular these days. So it can be defined as AI system that can create new content. This is where the name comes from. Generative AI, we can create new content. So basically, for generative AI, for sure we can do, but the main idea is not to predict something. Actually, we are predicting the next word, for example, in a text, but it is not as in we do in supervised learning. It is something that we create new content. It could be a text, it could be an image, audio, or for example, video, or code, even code we can create with generative AI. So the thing is that it needs to be run or trained by large data set to produce realistic and novel outputs. And also it is capable of human-like creativity. There are different algorithms, transformers for text actually, or NLP, natural language processing, or we can say GANs to use. I mean, GANs are using two networks, generator and discriminator. They are used to create like some produce some synthetic data. Variational encoders, for example, ways they are used to produce some images, videos, etc. Diffusion models, again, they are used to produce some images and new content. So autoencoders are for compression. So we will come to some use cases of this. So agentic AI is not new, but these days I have been hearing this in conferences and in papers as well, agentic AI. So it is not also an algorithm per se. It is a concept. What is the difference from generative AI is that it takes actions, it makes decisions, it plans actions actually. So I would say it is the combination of generative AI, reinforcement learning algorithms. It is the combination of everything. It can use the other ones as the tools for itself to make the decision, to take an action, to plan something autonomously, based on your needs, for example. Like as you see in the applications, autonomous research assistant could be one example for this. Based on this, you can, like, for example, do your research based on your like, for example, AI in wireless communication. This could be my title. Based on that, it can produce different research like ideas to me, or it can bring in the literature to me, so that it can use different tasks, different tools like different engines. Like this could be search engines, code interpreters. As I say, it could be generative AI, it could be reinforcement learning algorithm. But the thing is that it does something. It is goal driven. It is personalized algorithm framework for machine learning or AI, I would say. So with this, actually, I am done with the machine learning part, the different parts of different categories of machine learning. So then, is machine learning something new? Actually, it is not. So then machine learning is and machine learning and information theory, which is very relevant to wireless communication and in our field, they are very correlated to each other. That's why actually, like for example, information theories, it deals with how information is represented, how it is going to be transmitted, how it is going to be compressed, etc., etc. It used like entropy, mutual information concepts in information theory. Machine learning uses these concepts to represent the data, to understand the underlying behavior, underlying characteristics of the data. Like, for example, it comes to entropy or uncertainty. So in machine learning, we try to reduce the uncertainty, but in information theory, based on the application that we have, we also try to reduce the uncertainty in the data. For example, when we do encoding, like forward error correction, it would be very helpful for us to do so, as in machine learning. So also compression and learning. So these are the things, like, for example, mutual information in information theory says that how two random variables are related to each other. What are the shared information between the two? So machine learning uses this to perform some feature selection tools. As I said, like overfitting, compression. So then these two concepts, machine learning and information theory, they are pretty much correlated to each other. That's why actually machine learning fits in wireless communication. So considering the title of the presentation, actually, as you see here, it is all about the math. So it is not a magic. So towards 6G, what are the visions and standardizations efforts? So I'm not going to spend too much time on this, but like as a very historical perspective, we started in 1980s as 1G. For sure, we didn't call it 1G at that time. It was analog, voice-based, and there was no roaming because the different countries were developing their own systems, own networks, like in Japan, in US, etc. So then in 1990s, we met 2G, which becomes like SMS was introduced and it was also digital. So partial roaming was there. In 2000, 3G was, we saw 3G basically. So data was introduced. And also for the first time, like global standards have been introduced. So this is where 3GPP comes from, basically. Then 2010, it is 4G or AKA LTE. So then broadband is introduced. It becomes app industry. Everything is IP, all IP technologies. Like 5G 2020s, 5G is known for its vertical industries like agriculture, healthcare, finance, so on and so forth. And also IoT has been pretty much important or pervasive in 5G networks. Millimeter wave has become one of the frequency ranges that is used in 5G networks. And also vehicular to everything, it was the concept introduced in 5G. So in 6G, we will see what is going to happen in 2030, but there are for sure some studies going on. Like 6G, people have been saying that it is the first AI native generation. So then you have seen these charts a lot, I believe. So then these are from ITU, International Telecommunication Union. It is the vision of 6G in ITU's terminology. It is IMT 2030. So these are like on the left-hand side, we see the user scenarios. On the right-hand side, we see the capabilities. So there are some new things introduced for 6G by ITU. So, for example, when you zoom in, we see that there is AI and communication here. So, because this is the reason why I call that it is the first AI native generation, because AI is introduced in 5G for sure, but not from the scratch. When AI was introduced in release 15, there was no, I mean, there were some initiatives to do that, but people were not talking about AI-based communication in the beginning of 5G. But when it comes to 6G, we have started to talk about AI whenever we heard about 6G communication. So that's why AI and communication is included as one usage scenario in 6G networks. And also in these overarching aspects or design principles, it says ubiquitous intelligence. Again, this is something that we can refer to AI. AI, but I'm intelligence, aka AI, but it could be ubiquitous. It should be everywhere. So then this is the design principle. This is the challenge for us, how we can perform ubiquitous intelligence in 6G networks. On the right-hand side, again, in the new capabilities, by the way, the blue ones on the right-hand side, the upper half, they are the new capabilities introduced for 6G networks. And when we zoom in, we see that applicable AI related capabilities. This is also introduced for the first time for 6G networks. So 6G networks has many things related to AI. I mean, these are the ones that are directly related, but we can for sure relate the others to AI as well. Because all of them are at some point will be related to AI. What are the things? So when we transition from 5G to 6G, 5G in ITU terminology, it is IMT 2020. So we had eMBB, enhanced broadband communication. It becomes immersive communication. Massive machine type communication becomes massive communication. URLLC, ultra reliable low latency communication, becomes hyper reliable low latency communication. These are the incremental steps. So because as you know, in each generation from 4G to 5G, 3G to 4G, there are some incremental steps on certain aspects, but there are also something new introduced for specifically for that generation. As we said for 6G, these are like these design principles like sustainability, ubiquitous intelligence, security, privacy, resilience, connecting the unconnected. These are the overarching aspects or design principles. And also, again, AI and communication is included as a new user scenario in 6G networks, which was not available in 5G. So in addition to this vision from ITU, we can also look at the European perspective. So then recently there was a white paper published by some working groups at European, like from European, I mean, there were many authors from many European universities and industries. They came together and drafted this white paper. So then in their perspective, 6G use cases are these: collaborated robots, physical awareness, digital twins, fully connected worlds, trusted environments, immersive experience. Yes, there is no AI mentioned here, but when you go into details, actually they are all related to AI. In this one, it is not explicitly mentioned. There is no AI written there in this chart, but when you go in detail of the report, in all of them, basically in all of them, AI ML is mentioned as the enabling technology, basically. So again, from their perspective, what are the technological enablers? What we see is that network intelligence is there. Again, as I said, for the other ones that you see on the chart, we can refer them, like we can somehow tell the story from the perspective of AI, but network intelligence is directly related to AI in this case. It is the technological enablers for 6G network from the European perspective. So in network intelligence, AI native 6G architectures, this is the thing: zero touch management, AI driven air interface, edge intelligence, intent-based networking. These are all AI-based concepts that are introduced in this white paper. So when it comes to now, let's look at the 3GPP part. So release 17 and 18. So I specifically selected these things because my, I mean, on my one research interest is AI, but the other one is non-terrestrial networks. Actually, these overlap. These releases overlap with AI and NTN, because release 17 was the first release which is specifically explicitly mentioning about NTN integration in terrestrial networks. And also these are the ones that are heavily mentioning about the AI involvement in 5G networks. Release 17 and 18 are 5G, still 5G. I mean, 5G start, as you know, 5G started in release 15. So then when it was introduced, release 15, when it was released, so then there was a new function introduced, which is network data analytics function. So at that time, it was just this. So then there were no AI mentioned in that thing, but it was mentioning the network data analytics. So it was saying that, okay, there's a lot of data going on in the core of the 5G network, or core of the network before 5G as well. So then why not utilize these things? So then why not utilize these data in the form of data analytics? So what it does, NWDAF, Network Data Analytics function, by the way, it is located at the core of 5G core, 5G GC. So it can be done, it is for network optimization, predictive analysis, decision-making automation, quality of service improvements. But it does not do these kind of things, but it kind of enables these things. It was introduced in release 15, but it becomes much more important in release 17 and 18, basically. So it is important because it was the path towards AI and ML, NWDAF. It was the path towards AI and ML, powered intelligence. With these, 5G networks are envisioned to be more efficient, more resilient, and autonomous. So NWDAF, it can provide analytics to different network functions. It could be AMF, access and mobility function, for example, SMF, essential management function, or policy control function. So as you know, there are some when you decompose 5G core networks, so there are different network functions. So these are some of them, for example. So for the operations of these network functions, NWDAF can provide analytics to these network functions. And also operational and management part, it can be used to orchestrate the network. So when it comes to release 17, there were some enhancements to NWDAF. So 2 logical function components were introduced in release 17. One of them was analytics logical function, ANLF. The next one is the model training logical function, MTLF. So what these things are doing as written there. So then one of them is like kind of inference analytics derivation, service exposure, ANLF. So then it provides input to the MTLF to build some machine learning models, training and provision of trained models to further network nodes. So these are the important differences in release 17 and release 18. Then when it comes to release 18, there was another one, management data analytics function, MDAF or MDA. It is also introduced in release 17. It also supports network automation and intelligence. So the thing is that this guy, management data analytics function, it gets data from different sources. It could be NWDAF. Don't forget NWDAF for network data analytics. It gets data from different portions, and it also with the second, as you remember from here, with the MTLF, it can develop some AI algorithms, AI models. So then it can get input from these, and also for these it can automate the network. It can do fault management. It can do performance management. It means that this management data analytics function, MDAF, can utilize these functions that were introduced in release 15 and 17 to perform intelligent stuff in 5G networks, aka AI and ML, basically. So what are the things mentioned in as use case? What are things mentioned in release 17 and 18? First one is AI-enabled RAN intelligence. RAN intelligence, when it comes to RAN intelligence, network energy saving. So it is like cell switching, how we can switch the base stations in the network in order to maximize the energy saving in the network. So, but this, because the number of base stations or small cells are expected to be huge in 5G or 6G networks. So then this task is not a trivial task. So then it's a non-trivial task. So then we cannot perform these things with conventional simple algorithms. That's why we need intelligence. So also load balancing, because some portions of the network could be highly used, highly utilized, overutilized, but some portions would be underutilized. So then this should be balanced to provide kind of a, I would say, flat performance to many users in the network. And also mobility optimization, like for example, handover management. If we can predict the user trajectories or users' next base stations, so then we can perform some tasks prior to the real handover execution. And also AI for air interface. Again, these are introduced and mentioned in 3GPP release, in 3GPP releases. So one of them is CSI feedback. CSI, as you know, it stands for channel state information. So then there are two things mentioned here. One of them is the spatial frequency domain CSI. Compression. So it is like it includes two entities. One of them is UE, one of them is G node B. You know, as you know, base stations are called G node B in 5G terminology. So it includes two nodes. So instead of I mean, the main idea is to compress the CSI information in order to reduce the CSI overhead from the network. Because when we talk about MIMO, massive MIMO, millimeter wave communication, when we increase the orders of these, so then the overhead would increase significantly. So then we would need to reduce this overhead to make the network functionable, feasible, and manageable. So one of them is that. So then it is spatial frequency domain CSI compression. Other one is that time domain CSI predictions. This is to predict. So in this one, there shouldn't, I mean, two nodes. Only single node is enough for this one. It could be either UE, user equipment, or G node B. So then when you have the historic data about the CSI, so then you can predict the CSI instead of, and for these predictions, you can continue your operations instead of exchanging information, so on and so forth. Next one is the beam management. So then how we can select the beams. So normally, you know, in manual operations, we need to sweep the beams to look around, basically. Then we need to take beam measurements from each beams, how is between the base stations and UEs. And based on that, we need to select the beam, the best beam, which could be the best beam. So AI and ML can be used to best to select and also predict the best beam without doing all these boring stuff, initial boring stuff, like, I mean, beam sweeping and taking measurements, etc., etc. Also positioning. For positioning, we can use AI and ML to position the user instead of, like, for indoor environment, for example. If we can use some fingerprints, SNR signal to noise plus interference ratio, SINR fingerprints. We can use those fingerprints to predict that, okay, so if I get this SNR, I should be in the kitchen of the office, for example. Because normally you trained your algorithm with this information when you are in the kitchen, because in indoor environments, things don't change regularly. So then I'm more stationary. So when I'm in the kitchen, I usually get this SANR. So then if I'm getting this SANR, I should be in the kitchen. So these kind of positions can be done with the AI and ML integration. So it is not a myth from here, again, referring to the title of the webinar. It is not a myth, it is really happening. So what AI brings in 6G, motivation for AI, it's because like from starting from 5G and also followed by 6G, with exponential increase, it is going to be ultra dense network. So then there will be ultra dense users, like density of the users will be very high, density of the base stations, network densification is implemented in the network for 6G network, for 5G network. So this density brings new challenges for regular ways of or conventional ways of operations in mobile network, mobile communication networks. And also hyper connected, it means that basically everything is connected this time. So then we, if you remember ITU's vision, it says ubiquitous connectivity as well, connecting the unconnected. So it means that not only the people located in the city centers, urban areas, in rural, in remote areas, like a sheep in the middle of an ocean, for example, it will be connected as well. All these connections will create another problem for from the perspective of network management and orchestration. Heterogeneous things become more heterogeneous in this case. Like there are different types of base stations. Like it was like homogeneous previously, but types of base stations are different. Types of UE equipment, I mean user equipments are different. We used to have like just mobile phones or tablets or laptops. Now we have like wearables, we have sensors, smart homes, smart traffic, smart management, smart ports, etc. Smart X. So with these things, heterogeneity is increasing in the network, and also massive device connectivity comes hand in hand with this. So, and also integration of terrestrial networks with non-terrestrial networks. It is also a challenging, really challenging. It is promising, but at the same time, it is a challenging task. So we cannot perform, we cannot achieve these things. We cannot manage our networks with our regular operations. We need to revolutionize. I couldn't say that thing. We need to use AI in 6G network. So in order to manage network more efficiently, basically. Okay, what is the other thing? So then there are emerging technologies. For example, these days we have been hearing a lot about reflective intelligent surfaces, RIS. So these things are posing more challenges. They are bringing their own challenges to the network, because in normal, like in legacy networks, in 5G, in 4G, 3G, we haven't seen these such kind of things. We had relays, but we didn't have such kind of intelligent surfaces. So then they are bringing their own challenges. They're bringing their own complexities to the networks. Terrestrial communication is a complete different story. So then it is not confirmed yet, as far as I know. Terrestrial will be used in 6G, but people are speculating around it. But when it comes, so Terrestrial is, as I said, it's another story. So it will bring many challenges, many complexities. Yes, it will bring a lot of why we are trying to use it, why people are saying that it should be used in 6G, because it has abundance of bandwidth, but for sure on the dark side, it comes with lots of challenges. Integrated sensing and communication, ISAC. It is also a promising concept, but yes, when we use the communication at the simultaneously with the sensing, so then there will be more complexity in the network for sure. And as you see, for the incremental steps from 5G to 6G, we have even more stringent requirements. I remember when it was when we were talking about 5G, we were saying that stringent requirements of 5G, etc., etc. But this time it is going to be even more stringent, harder requirements in terms of latency, mobility, energy efficiency, data rates, peak data rates, etc. So actually everything started from here, like cognitive cycle. So we need to act based on this cognitive cycle. So cognition, intelligent and cognition sometimes used interchangeably. So they are very close concepts. So then there is this Joseph Mitola, maybe Joseph Mitola tree, maybe some of you know him. So he is kind of founding guy for cognitive radios. So he has a PhD dissertation on that. So this was the cycle introduced by him in early 2000s. So first we need to observe, based on that orient, plan, decide, and act. So then it is very similar to what we are talking about. Like if you remember a couple of slides ago when we were talking about agentic AI. So then this was mainly the same thing with agentic AI. So observe, we can use base station sensors, use the devices to collect data, orient, so then to understand what's happening. There is a congestion. It is due to mobility or interference, for example. So then we can plan accordingly for handover, for spectrum allocation, beamforming, power control, etc. We can decide which cell should serve the users, or which UAV should be deployed, or UAVs should be deployed at which location in 3D. Act, trigger handover, reconfigure network slices, for example, reroute the traffic based, or move the UAV towards the density of the users, and learn. So then experience, build an experience. So then why this happened? So then I took this action and this happened. Learn from the experience. So AI capabilities for 6G, context awareness is one of them. So AI is aware of context. This is pretty much important because in normal operations, as you know, it is context unaware structure we have in mobile communications at the moment. When you're unaware of the context, you cannot be efficient, basically. So yes, it could be somehow simpler, but trade-off is that when it is simpler, so then most of the time it is not efficient. But for 6G network to handle all those kind of stuff that we mentioned, all the challenges, all the requirements, we need to be as much as efficient as possible. So real-time intelligence, it means that we need to act in real time. I mean, it is not something, okay, this is the condition, so then we can train our algorithm, we can build an algorithm, we can do this, we can run this algorithm, etc. Then we can respond. So this is not the case anymore. So then it should be real-time intelligence, real-time response. Predictive capability that AI brings in 6G. So then, which is very important, if you can predict the future, as we do in, for example, if you remember from release 17 and 18, CSI prediction, for example, or beam prediction. If you can predict something, so then you can plan accordingly. You can plan beforehand. The things are really happening. Adaptability, it can adapt the network. So normal conventional algorithms, they cannot adapt. They need to be run from the scratch most of the time, usually. So when things change, which is very common in wireless communication environments, so then they cannot adapt, but AI algorithms can adapt if designed properly. They can be scalable as well. So then when you increase the network size, they can be scalable based on the design again. So I'm not saying that all machine learning algorithms are scalable. It is completely dependent on the design that you are doing. Distributed learning is one plus. With federated learning, it becomes even more secure and more efficient. Model-free design is another plus because you don't have to know the model of the environment in advance. So which is the case in wireless communication. I would like to introduce one thing here, AI for 6G versus 6G for AI. So because these two go hand in hand. So AI for 6G, these are the things that we have been discussing. AI can be used for 6G network to manage the radio resources, manage the mobility, reduce the latency, self-organized network. As I said, proactive management, dynamic environments. It can deal with them very efficiently. These are all okay. We will delve into these things a little bit more. But when it comes to 6G for AI, so it is not just one way. It is not half duplex. It is actually full duplex. So AI is good for 6G, yes, for sure. But 6G is also good for AI because 6G is promising massive connectivity. It means that everything will be connected. It means that there will be more data, as well as ubiquitous coverage. Everywhere will be covered, As I said, now AI can collect data from the ship in the middle of the ocean, which is normal, maybe not possible. So then you can get the data from there. So then you can increase the amount of the data, but at the same time, you can increase the diversity in the data. And also extreme data rates and low latency, these are kind of enablers for AI. For example, virtual reality, extended reality, augmented reality applications, these are which are AI based. So then these could be, and also distributed AI processing, which is promised in 6G networks. There will be it is going to be an enabler for 6G networks. As I said, AI is a core enabler for 6G, but 6G is creating infrastructure for AI. When we talk about when we talk in front of the Carleton University NTN lab, so it would be pity not to mention high altitude platform stations hubs. So hubs, for those who don't know, they are radio stations located on top of an object like a balloon, like an aircraft. The altitude would be around 20 kilometers from the Earth's surface. So then they are called near space, or because they are located at the stratosphere. Say they don't orbit. They can be, as I said, free floating balloons, airships, or powered fixed wing aircrafts. Why I mentioned it here? So then because with HAPS, it is not only ubiquitous connectivity with HAPS because the footprint is huge. With HAPS, we can talk about like 500 kilometers radius footprint when it comes to HAPS. Not only that, not only providing connectivity for unconnected, connecting the unconnected, but also it can serve as a database, like a server in the sky. So then it can bring the content closer to the user, for example. And also because of the weather conditions in that altitude, so then it could be very efficient in terms of running the server. So then it could be an interesting enabler for AI in 6G network. When we talk about 6G for AI, HAPS could be one enabler. Okay, some use cases. So I know it is already too much, so I will try to be as quick as possible. Radio resource management could be one option. Efficient allocation of spectrum, power, or beams. So then these are radio resources. Radio resources, as you know, is not just the bandwidth. So it could be a power or beams. So then if we use them efficiently, that's plus. Because when we, for example, we said maybe terrestrial communication would be introduced in 6G or even 7G. I don't know why we are doing this to increase the bandwidth available for mobile communications. But this is not enough. This has never been enough. Like introducing new bands has never been enough. There should be like a full-fledged solution. Full-fledged solution is this. We are enhancing the capacity by introducing new bandwidth, okay, but we need to use it efficiently because that bandwidth still not sufficient to provide all those things, because when you increase the bandwidth, at the same time the demands are increasing. When you increase the bandwidth linearly, but demands are increasing exponentially. So this is the problem. So the increasing only the bandwidth or resources is not sufficient. At the same time, we should be efficient. So then radio resource management is the concept dealing with these kind of things. Challenges, yes, we have, as I said, spectrum scarcity, demand is increasing, and there is an interference that is limiting our capacity, basically. Throughput, channel capacity, it can also, as you know from the channel capacity formula, it can reduce our channel capacity. So when the channel capacity is reduced, so then the overall capacity of the network would be reduced because throughput is less. So then when you are running, like for example, high bandwidth applications, so like for example, the one that we are doing here, like video conferencing. So then you would not experience very good service in such cases. So then, but the problem is that in 6G, there will be even more challenge because we said there will be massive communication, even more than massive machine type communication. There will be massive communication. It means that the number of connected devices will be increased dramatically. So this is the problem. So then heterogeneity is another problem. So then we normally had like terrestrial networks. Don't take aerial or satellite just as base stations because they are also users. So then imagine like think take the cargo drones example. So then they will be users as well. It means that there will be diverse set of users and also with increased amount. So these are the things we need to use them, as I said, as efficient as possible. There could be different things, predicting the interference and mitigate accordingly, like avoid the interference. Like for example, frequency hopping. You can, like if you can, for example, you can use AI to predict that okay, there's an interference at some point. It could be a jammer, for example, in military application. Imagine you are with like you are sending a drone to a particular location, and that in that location there's a jammer. So then because of the jammer there's a huge interference that you are experiencing. If you can predict that, if you can detect that with the use of AI and ML, so then you can just hop onto another frequency band to avoid that interference. Or not only not it doesn't have to be a military application in other applications as well. If you are experiencing interference in one band, you can hop to another band in order to avoid interference, but this can be enabled by AI and ML. So I just want to mention one of my previous works in my by the way, my PhD was related to AI-based wireless networking. So this was one of the works that I have done. So because I intentionally brought this work into this webinar because it is a very good example. Because it has all types of, like all back in time, the ones that were available, all types of AI categories, and also it is related to radio resource management, and also it is context aware. So then I guess it is a very good example. So as I said, Mitola 3, it is like cognitive radio. Cognitive radio is the concept is that, okay, there could be some licensed users, we call them primary users, they can use the spectrum freely, like yes, they get the license and they can use, and they have the priority to use the spectrum. But there could be also secondary users, SUs, they can use the spectrum opportunistically. It means that they need to sense the spectrum. Not only this, cognitive radio could be used in the example that I have given about military drones, for example. It is also cognition. It is also cognitive radio. You need to hop in different frequency bands according to the condition. So in this example, the secondary users, SUs, need to understand they can use the spectrum opportunistically. It means that if this frequency band is available, they can use it. But if PU comes in, so that they need to evacuate the channel. So then they don't have any priority. So regular process is that, okay, you sense the spectrum. When you detect the PU, you need to evacuate it. You need to decide the spectrum. You need to share the spectrum with other SUs, etc., etc. There is a very cumbersome and inefficient methodology introduced in this. But what was like what I mean, the predictive one, proactive. So before going into that, I can say this: spectrum sensing phase, which is the first phase. You need to sense the spectrum, to identify the frequency bands that were available. First, this is the first step and most time-consuming phase, actually. So then you need to deal with this phase to get rid of like time-related issues. So proactive spectrum sensing was already introduced. So they are saying that, okay, we have this frequency band. If we have the historic data about that channel, frequency channel, specific channel, so we can make the predictions according to these predictions. Maybe if we predict that, okay, that band will be occupied, so then the secondary user won't go there and sense it, don't spend time for that, and it can use its time for the channels that are more likely to be available. So this is good. This is okay. So, but there was one problem with this approach. For this, you had to have historic data for each and every channel, and each and every location. Because whenever you are, if you are a mobile, whenever you change your location, you need to have those information for all the channels available around you. So whenever you move, again, you need to have all these information, historic data. So which is not feasible, which is not realizable, right? So because it is against some physical conditions like memory, complexity, etc. Instead of this, what I proposed, what we proposed. So instead of using the historic data of specific individual channels, we can take this to a higher level to radio access management, radio access technology. Like, for example, there's a 5G base station there, there's a 4G there, there is some other like Wi-Fi there, available there. So then there are different radio access technologies. If I can know the traffic loads of these things, historic traffic loads, which is more feasible because for the base station, it is already logged. We have that. So then I can make the prediction. So this was the first novelty that was brought in this work. And also quality of based optimization. So normally what I do, okay, I sense this first, I mean, I find after spectrum sensing, I find, for example, five bands that are available. But then based on my quality of service requirements, I select one of them. So the question is, why did you sense the one that is not that doesn't fit into your requirements at the first place? You shouldn't have sensed that at the first place. So this was the idea. So first I get the requirements, like service requirements from the users. Based on that, I use reinforcement learning algorithm, and also I do the time series analysis for the traffic loss of radio access technologies. Based on all these things, I run a reinforcement learning algorithm to decide which band to sense. That band, if it is available, would be the band that I want to use. So then I don't have to sense many bands, then select among them. It is an inefficient method. So this was kind of a system model that I have. So then there was an SU. It is within the vicinity of, like, for example, 4 different radio access technologies. So what is done? So then first, as I said, I have used back in time, these were the categories that we had. We didn't have agentic AI, generative learning. We didn't have federated learning. I mean, different versions of federated learning was there, but not specific to federated learning. So unsupervised learning, what I did, I had the data from the Milan City, Italy. So then it was like there were like square shaped grids, 10,000 square shaped grids. They divided the city into 10,000 square shaped grids, like with a dimension of 235 meters. So now for each grid, they logged the like SMS, like telecom telecom activities for every 10 seconds. Anyways, this could be a problem. 10,000 grids for 2 months, then there were a lot of data. So instead of this, what I did, I first clustered the data. So then I found the ones that are similar to each other with the clustering by using unsupervised learning, by using k-means. First, I clustered them. So then I ran artificial neural networks to do the time series analysis to make the predictions by using the data from the grids that are similar to each other. So then first thing, I could use all the data. There were one problem, complexity problem, training time. There could be different things, like, because there would be different, like diversity would be more than enough. So then there could be underperforming. And also the main bottleneck was the computation complexity. If I used only a single one, so the amount of data was not enough. At the same time, the diversity was not sufficient. So then this was a very good strategy to do prior to the prediction, training the algorithm for time series. So then I did the predictions by using these predictions, and also getting the requirements of the users as inputs. I did band optimization in this work. So okay, there could be a mobility management as well. I'm going to be as quick as possible. So traditional schemes are reactive, rule-based, and they're reactive. It means that they react to the changes. But when we talk about AI and machine learning, we are talking about proactiveness. So prior to the things that are happening, prior to the changes, we act. So this is the proactivity. So, but these traditional conventional methods, they are reactive. But when there is a rapid context changes, when as in the case of like vehicular networks or UAVs, or there could be seamless service continuity. For example, there could be mobile multi-access edge computing stuff. So complex user patterns, user behaviors, dynamic network topologies. There are different things. These are the problems for mobility management, because when we are talking about mobility, it means that things are changing. When things are changing, regular conventional algorithms are not sufficient, so then we can use machine learning or AI algorithms, proactive handover management, user trajectory predictions, as we talked about 3GPP releases, mobility across NTN, mobility aware resource allocation, clustering, profiling, beam management, as we again discussed these things in 3GPP standards. So the thing is that we can predict the things in advance. So then based on that, we can plan and we can act accordingly. Like just just to give an example of handover management. So normally, as you know, there are many entities are involved in during the handover preparation, handover execution, etc. So then there's an UE, there's a target base station, there's a serving base station, there's a core network. So then there's a lot of overhead between these entities in regular scenarios. The thing is that we are very limited in terms of latency. 6G networks are reducing the latency requirements. 5G already did. 6G networks are further reducing them. So with these requirements, we cannot do this. So then all this overhead is a problem uh, in terms of complexity of the network, and also like bandwidth utilization is a problem when with the overhead, and also at the same time they are taking time. So we need to get rid of this. If we can predict the next base station of the user by predicting, for example, trajectory, but if we can predict that, so then we can do many things that can be done in advance. Some things cannot be done in advance, but we can perform the tasks that can be done in advance with the use of these predictions. So then this was another work that we have done for millimeter wave communications. So we were trying to optimize the throughput, but when it comes to throughput in our formulation of the throughput, so then there were like time handover cost. Handover cost is the time that is spent during this handover. So then it is in the denominator. So then it is adversely affecting the system, impacting the system performance. So that basically we were trying to. When I say we try to maximize the throughput, actually you can take this, interpret this as minimizing the number of handovers. So then we were trying to find the best base stations to be connected with during the trajectory of this UE. So then we use different, I'm just going a bit quick. So then we use different algorithms, double deep Q learning we used. We tried to maximize the user base station connection durations in order to reduce the handover cost and number of handovers. So the problem is that when it comes to 5G, so there were small base stations with smaller coverage area. With these, so we can expect more handovers, and also we are saying that there will be NTN integration, like satellite, LEO satellites. When it comes to LEO satellites, handover is kind of inevitable. Like frequent handovers are inevitable. So then we need to address this problem in our solutions. So I just fast forward. Energy efficiency as introduced in that. So then we are trying to connect everything. It means that we need to increase we need to densify the network. When we densify the network, it means that more base station deployment, base station deployment is can be interpreted as more network energy consumption. We need to deal with this. We need to address these things by using some dynamic power controls, sleep modes, intelligent sleep modes, traffic aware resource allocation. All these should be done or can be done with AI and ML. So if we want to address these challenges, AI and ML is inevitable. It is not kind of we should, it is a must. Cell load estimation is another problem that we did with Mariam. I believe she is here. So this was one of the work that we have done. So we addressed the problem of cell load estimation. So because we said like in 3GPP releases, network energy consumption, network energy saving. Under that, cell switching is mentioned. But the problem is that in the literature, the measure that the works predominantly assuming that they know the traffic load of sleeping base station perfectly, which is impossible. When you put the base station in a sleep mode, how can you know its traffic? But in literature, this is the assumption, which is not realistic, which is not feasible, which is not realizable. So then we are trying to address this problem. So then how we can know the base station, the traffic of sleeping base station. We implemented different algorithms, statistical methods like averaging, or like neighboring algorithms. And also we used like sophisticated algorithms like LSTM, long short-term memory algorithms to predict the time series because they are powerful tools to predict time series data. So in our problem, it is the time series analysis as well, because we want to predict the next time slot, the traffic load of the sleeping base station at the next time slot. But this is not the same problem of the proactive management. Proactive management is another story. They look similar to each other. This time the problem is that we don't know it. In proactive one, even if you cannot do proactively, next slot you will know it. But this time, next time slot it is sleeping. You cannot know the traffic. So it becomes a must. In the previous one, yes, it would be better to do that. But this time it is something that we have to do because we don't know the traffic because it is sleeping. So there could be different problems. So then estimation errors will be associated to the estimation methods that we have. So, but we try to show how these things affect the performance, cell switching performance. Another work is like how these things, so with the work with Mariam, with this work, we try to solve this problem. So then we try to estimate the traffic. But in this work with the young researchers that Professor Halim Yanık mentioned, my undergrad, now they are graduate students, but at that time they were undergrad students. So then with them, we investigated the impacts of errors in estimations of traffic loads. We used here two different Q-learning algorithms, full state design and a lightweight state design. So then I won't go in detail. So we use Q-learning basically, but we designed two different Q-learning algorithms to say that, okay, if you want to, so there was a trade-off, complexity, performance. If you prioritizing performance, use FST. If you prioritizing the complexity, use LST. Both is good at some point. So then based on the needs of your network, these are the two different algorithm designs. So again, with Mariam, we have this multi-layer cell switching. So we said, okay, if it is going to be a cell switching, by just using tier one, we can use UAVs. Yes, there were some works just using UAVs for cell switching. We said, okay, we can use HAPS. Yes, we have been doing. We have one of the first doing HAPS-based cell switching, by the way. Yes, we can do HAPS-based cell switching. Yes, we are already doing that. But why not to combine all of them at the same time? Why not to utilize the full potential of multi-tier network formation, basically? So this was one of the initial ideas of using satellite networks for cell switching network energy saving, but there are some associated problems, challenges like latency for example, imagine you are using geo satellite. What is going to be latency? We are talking about 500, 600 milliseconds. So it is going to have an impact. So then when we have multi-tier, normally in terrestrial network, when we do cell switching, we are not talking about the latency. But this time we have to talk about the latency. We discussed how this could be how AI can be used in these things, and also how generative AI can be used in this. Role of generative AI. So there are different things to discuss here. So with generative AI, so I quickly come to this work that we have done with Afsun and also my two students, Görkem and Berk. So we used AI for demand shaping here. So then I want to basically show this one. So how it is gonna work. So there is a demand. So this idea emerged from the discussion of disaster communication. So when disaster communication happens, usually we talk about the insufficiency of the network. Today we had an earthquake in Istanbul, so that there were problems with the mobile network operators. So whenever this kind of disaster happens, we talk about, okay, network, we need to somehow boost network capacity, we need to deploy base stations, we need to restore the damaged ones, etc., etc. But the idea is, why we are just talking about the network perspective? We can maybe do something from the user perspective. So this idea comes from there. So then it got improved after discussions with the co-authors. So the idea is that, okay, is the first demand labeling. This can be done with generative AI as well. So can we it doesn't have to be generative AI, but it can be done with generative AI. Demand labeling. Is it a critical or non-critical data? Imagine in a post-disaster scenario, there are some rescue and search and rescue teams, SAR teams. Their communication type should be critical because they need to be connected all the time. So then we cannot intervene with their communication. So then if this is a critical communication, we need to conserve the meaning. And also we don't reschedule, because when if it is non-critic, we can reschedule. Imagine you are in a post-disaster scenario, but you are not affected. You are at your home, like you are sending some funny pictures to your friend. So it is not the time, so it can be delayed. So then we can send it to in the midnight, for example, when the network congestion is not there. So we can reschedule it. We can strategically, we can intelligently label the data. We can understand the context. I'm talking about some kind of semantic communication. We can understand the context. Based on the context, we can act accordingly. So agenting AI, just to refer to that one. So, okay, we can reschedule it. If it is not rescheduling, we can compress it. So we can, like, for example, if it's a video, maybe we can summarize it in text and send an SMS. If the video is not that critical, if only the meaning in it is important, so then we can extract that meaning from the video and we can send it as SMS. So this was the idea. So we identified several use cases with generative AI. For example, as I said, disaster communication was one of them. It is a pretty important one. So the idea is so the thing is that we need capacity. There is some limited capacity. From the network side, we can increase this capacity by restoring base stations, by putting NTN elements into the network, etc. But on the other hand, we can reduce the amount of demand as well to minimize if you can minimize the demand, so then we can make use of this available capacity more and more. This is the idea. So then this was already discussed with in this previous slide. So then we can also do network energy saving. So the idea is that, okay, capacity is everything in cell switching. This is the underlying idea that we have seen in our many works. So, but if the base stations are overloaded or they are loaded, so then we cannot offload traffic to them. So then we cannot switch off more base stations. It means that we cannot save more energy. In order to do that, maybe we can compress the data from the user perspective. So then we can we can relax the traffic load of the base stations so that we can switch them off. Basically, this is the idea. But the thing is that we need to preserve the meaning. So then these are some of the challenges. And also interference management. This is the expertise of Afsun. So then how we can also reduce the traffic from the backhaul of the network. So for example, this is for load balancing. Sorry, this is for load balancing. How we can reduce the traffic of the mm, traffic at the backhaul of the network, so that if we can reduce that, we can distribute the load in a more balanced way in the network. And also interference management, if we can reduce the again, the idea is reducing the traffic load. If we can reduce the traffic load, we can optimize the radio resources more efficiently, so then we can avoid interference, we can get rid of interference, and we can improve our throughput, for example. There are challenges. So then, for example, we are saying that, okay, sustainability, we are going to reduce the network energy consumption, but we are doing generative AI. So then there should be a it is a kind of a double-edged sword. We shouldn't be increasing the energy consumption of the so okay, if it's not from mobile network operators, it is fine. It is not the idea. So then we should reduce the overall energy consumption. We need to measure it. If we are causing more cost in terms of energy consumption when we apply these things on to reduce the energy consumption. I mean, if we are consuming more energy to reduce the energy, so then it is not, it doesn't make sense basically. So some enabling technologies, the on-device AI, there are different manufacturers, vendors have been doing this already, like Apple, Samsung, and other vendors as well. They have been doing this, so they are bringing the intelligence at the device. So then, if it is at the device, so then we can use it more efficiently. We can do all these kind of things. So then it can be done with the context of small language models, SLMs. So we have large language models, like ChatGPT is one of them, but it is too much for a single and poor mobile handset. So then there are some counterparts called small language models, lighter versions of them, but they can do similar things, basically. So challenges, there's data privacy. So there's scalability issue. So then how we can solve the scalability? Yes, we said machine learning is good for scalable, is in terms of scalability, but it is based on the design. So then how it could be designed. Generalization is one thing. So then how we can train our algorithms to be more generalized, not just for a specific problem, because it is a inefficient use of resources. So then we need to build some AI algorithms that can serve to many entities, many different scenarios, many networks, basically. So real-time responsive is another problem. So if it is online learning, if you keep learning, and if this learning time, training time is taking too much time, so this is also a problem, because we are talking about hyper reliable low latency communication. It means that the latency should be basically minimum. Energy consumption is another thing. As I said, we shouldn't be increasing the energy consumption of the network for the sake of decreasing the energy consumption. So then it is kind of a dilemma. So we should be careful about this. Regulatory and ethical perspective is another thing. So then there could be a bias. Transparency is important things. So then there should be a global compliance, global regulations. I know that there are some regulations. So they are the first initiative. They are first regulations in about AI. So in European Parliament, European Commission, there were some AI regulations. I guess US will follow some. I'm not sure from now on, but it was planned, some regulations from the US as well. So yes, there would be different things, research needed against complexity, scalability. Quantum is another thing. So then quantum can make the AI and ML more manageable. Quantum computing, quantum communication can make it more secure. These are things. So yes, there are different research how it can be applied in terrorist communication, risk technology, etc., etc. So if we come back to our original question, what is AI? Actually, AI is all of them. AI is not just one. AI is all of them. So we shouldn't underestimate AI. but on the other hand, we shouldn't overestimate it. Thank you for listening. I'm always open for questions and new ideas. These are my contact information. Please feel free to contact me. Thank you.
Thank you, Professor Metin, for the great talk. Also, we went extra than the allocated time, but I didn't want to interrupt because I was also learning a lot from the presentation, and I'm sure that also the attendees learned a lot. So before we ask the attendees to ask questions, there are two questions in the chat that I would like to read them. Um, One of them is that how the generative AI can produce novel ideas while they have trained on something that is already existing. Or maybe the question is raised by Mohammed Mahyoub. If further clarification is required, maybe he can unmute and also ask the question.
Is it in the chat, Afsun? I don't see it.
Yeah, that's in the chat and by
I'm
Mohammed.
wondering how generative AI can produce novel ideas while they have trained on existing. So it is the thing. So for example, maybe I'm not sure if you are familiar with YOLO, you look only once for image recognition, for example. So for those are pre-trained algorithms. So if you want to find a human face, for example, with those algorithms, it can do it immediately because it is already trained for that. Or for other things, like if you want to classify the fruits, for example, the different well-known things. But if your algorithm, if your problem necessitates something new, so then you need to train their algorithms. But the thing is that these algorithms are already trained, so you can find something similar to yours and you can update it, or you can do from scratch. Uh, there was an idea about this, I guess, telecom large language models. So then there could be, we can basically build some large language models just for telecommunications. So in that, they can be built for radio resource management, for example, but you can take the same experience built for that and you can use it for mobility management. But for sure, if it is not exactly fitting your problem, you need to update the parameters with the new data. I hope I
Thank
understood
you
the
very
question
much.
correctly.
There is also another question, which, from your perspective, which machine learning technique stands out as the most suitable or promising for optimizing the configurable intelligent surfaces in next generation wireless networks?
So, so there is a one rule for machine learning, so that there is no one solution for all the problems. So having said that, the thing is that what kind of things you'd want to do. If you want to optimize, for example, the phase shift of those kind of things, there could be different methodologies. There, deep learning can be used, but reinforcement learning can also be used. In my experience, for many problems, so this is the thing. First you have the so if you need to have some ground truth. If you have the ground truth, you can develop some deep learning algorithms. It means that you have the input data in an offline manner. You can run this normally inefficient algorithm with that input. Then you can produce the output. Then you can create your data set with this. Then once the data set is created, you can predict new things with that. But my experience says that this is not very efficient method because it takes too much time, and also most of the time in our works basically it doesn't perform as well as reinforcement learning algorithm. So if it is optimization, I would mostly suggest reinforcement learning algorithms. And if so, it's a good question basically. If it is a simple problem, don't use sophisticated, more advanced algorithm. This is the number one rule for me. So if it is a very small scale problem, just use vanilla Q-learning. But if the so based on observe the problem, so understand the problem, the necessities of the problem. Based on that, reinforcement learning is a good resort. But in that, you need to decide based on the requirements of the problem. You need to decide which kind of algorithm that you need to use. As I said, if it is small scale, vanilla Q-learning. If the states are increasing, you can use deep reinforcement learning. If the number of actions are increasing, you can use actor critic. But having said all these kind of things, there is no single solution. So you need to try.
Thank you very much. So I see Mohammed Mahyub raising hand. Yeah, please go
Yeah,
ahead.
nice.
Thank you very much, Dr. Metin. I really appreciate that, and I really enjoyed the presentation.
Thank you.
It's informative presentation. A lot of things I have learned. Maybe I can revisit my question regarding the novel ideas. In one of your slides, when you presented the generative AI, you mentioned that generative AI could produce novel ideas. But my question here is that how can we expect new ideas from something trained on uh, something exists, right? AI, you turned it in data exist there, the ideas that will be used already there in the future. And then are we expecting new ideas really? And can we rely on these new ideas, novel ideas that can be, brought by these generative AI models?
I guess now I understand your question. Sorry, it was in the beginning I didn't understand when I read that. Okay, it's a very good question. So generative AI is a very new thing, so we cannot rely on that. We cannot fully rely on that. This is for sure. Even when we see from the 3GPP perspective, they are very conservative. We have been talking about AI and in many different domains, but they are very careful of picking the use cases and scenarios. Here, when it comes to your question, so for example, in our case, we use off-the-shelf algorithms to reduce the demand. For example, compression. So compression is built for something exists, as you are saying that, but I can make use of it for the telecommunication. Why is that? Maybe I can compress my data. If it is a video, for example, I can compress it and send it to the send it to the network, so that if I compress it, I can save from the bandwidth, save from the spectrum. Similarly, so those algorithms that can extract information from, for example, video. So then I can convert their format from video to text. So this is for normal thing. You can do it for your own job. For example, you have a very long video to watch, but you don't want to watch it. You can just convert it to a summary text. So then here you go, you can just read it. So this is your application. But from telecommunication perspective, I can do the same to save the spectrum. This is how we can, so these are the tools that on top of these tools, we can build something new. So then I am not saying that we can do something novel in them, so that it is also possible. So you can do sophisticated generative AI algorithms for telecommunications. This is okay, but you can also make use of those off-the-shelf algorithms for your needs. One more example. So forget about generative AI. As I said, face detection. Face detection is done for other things, for many different domains, but we can use it for our purposes, right? So, for example, if I put a camera in front of the campus, in front of the building, for example, Minto Case building. So then I know your office. For example, imagine you are alone in your office. So I can switch off the radio in your office when you are leaving. But as soon as I detect your face when you are coming to your office, prior to your entrance your room, so again I can turn it on. So then as soon as you are there, it can be ready for you. You see, this was developed for some other purposes, but I can make use of it for my purpose from the telecommunication perspective. I hope this is. I want to
Thank,
talk more, but I also.
thank you very much. Really appreciate that.
Thank you.
Thank you very much. So any other question from the participants?
By the way, sorry for exceeding the time.
I have another question, but I'm waiting for someone else. If anyone wants to participate, I really like the presentation, and I'd like to utilize this remaining time if it's possible.
You can call me as well, Mohammed.
That's good. Okay.
So I assume that there is no question from the participants. So Mohammed, maybe you can go ahead with your question.
Yeah, I'm not expecting for this question a comprehensive answer. Of course, it's outside this presentation, but somehow related. Given that many features and characteristics of 6G are already taking shape, and we know many things about 6G, are there any insights into what 7G might look like and what potential requirements and technologies can we expect for 7G?
Mohammed, I'm really sorry I lost you at some point, so then I didn't understand quite well.
I'm asking about the potential requirements, what we expect, and technologies for 7G. We already know the
7G,
shape
okay.
of 6G, right?
Okay. Okay. To be honest, I really don't know, Mohammed. To be honest, we can speculate about it, but for sure it is too early for that. I cannot answer that question, but I can tell you this: there are some speculations. There are some debates about this G trend as well. So there was an article about jumping off the G train, for example. I remember the title. So then why we are using these G things over and over again? So then why we are struggling with all these problems? So maybe there may not be a 7G as well. I'm not fully sure, but there are these kind of discussions. But in terms of technology, for example, when you ask me this question about 6G, I was not aware of, like, no one knew about this reconfigurable intelligent surfaces at that time, but now it is one of the main topics. But what I can say, so normally if a technology is introduced in one generation, it usually goes to the next G. So for example, AI is, we say native AI for 6G, probably it's not going to happen, but we see the full potential of AI in 6G, 7G probably, because remember 6G is going to be kind of full, the first generation with native AI. So it means that native AI will be in 7G, in my understanding. So another thing is that quantum computing. So these days, I like if you go to the conferences from communications, so then there's a lot of discussions about quantum things. So, but people are it is a pretty much slow pace. It is progressing with a slow pace. So I don't think it can be realizable in 6G, maybe 7G. What I can say, full potentials of AI and quantum technology would be my guess. But my guesses are usually are not good, because I said at the time, I said Instagram wouldn't be good. So then, uh, so my don't try my guess actually.
I'm writing a paper now based on your talk, by the way, based on your advice. Don't fall me down.
Okay, so thank you very much. And there is also another question in the chat, and maybe we consider it as the last question because the event has lasted for almost 2 hours. So that's about the AI ML in a space. So that means in satellites or hubs. And the question is that in a space we have more challenges like less energy consumption, less memory, more autonomy is needed also, and also there is more mobility. So he's actually asking for your insights about using AI ML in space.
I think the examples are satellites and hubs. I think we need to distinguish them, because when it comes to satellite, even we need to distinguish the level of satellites, LEO, MEO, or GEO. So when it comes to LEO, things are very chaotic. So very high speed, I mean the velocity of the satellites. So things are very challenging there. But when it comes to hubs, things are not that challenging compared to LEO satellite, because it is kind of stationary, more feasible for AI and ML implementations. What I would say, the thing is that I think the combination of HAPS with satellite networks would be the solution for AI and ML integration for satellite networks. Not only for HAPS, but the integration with HAPS and satellite is going to be the solution for satellite networks, in my understanding, because we can take the servers to the HAPS as well. For the orchestrations of satellite networks, maybe the entities at the hubs can help to like predict the things, optimize the things for the satellite networks. Yes, for satellite network, it is very hard to like deploy a model on top of them. It is going to be very hard for sure. It is going to be performed probably through the ground stations, but instead of ground stations, we can take the models, take the computations closer to the space with HAPS. I would see the HAPS as the solution.
Thank you very much, Professor Metin. And also thank you all the participants. I really learned a lot. And yeah, that's the end of the event. And also many of the participants asked for the slides. I wanted to check if it is okay also to share the slides with the audience.
Sure, sure. I can
Okay,
send it to you.
so
Maybe you
yeah,
can.
thank you. Okay, yeah,
Thank you.
thank you. And thank you, everyone. Yeah, have a good day and have a good night. Thank you.
Thank you very much. Thank you. Bye
Bye
bye.
bye.